Hello everyone, my name is Alan. I'm from the Robotics Institute of Carnegie Mellon University. Today I'm going to introduce our paper titled Towards Robotic Assembly by Predicting Robust, Precise, and Task-Oriented Grasps. So what is a good grasp in manufacturing settings? First, this grasp needs to be robust in terms of lifting up, because if this grasp cannot even grasp the object in hand, it cannot do any downstream tasks. Second, it needs to be precise in terms of the in-hand object pose. Here, this object was displaced because of the grasp, and if the downstream task doesn't compensate for this displacement, it won't be successful. Furthermore, it needs to be suitable to the desired task. Here, we're doing a bracket cone insertion. We don't want the robot to grasp too close to the insertion point because the gripper would intervene during insertion. So a good grasp needs to be robust, precise, and task suitable, as shown in the last video. The whole problem can be divided into three sub-problems. The first one is to estimate grasp robustness, which is the ability to pick up an object. The second one is to estimate post-grasp object shift. Doing this can guarantee a precise grasping. The third one is to estimate task performance for grasp to ensure that such grasp is appropriate to the task. We design one neural network to solve each of the sub-problems, and we cascade them to filter grasps until we get the best one that should satisfy all three constraints. Here is the architecture of the three neural networks. They all have the same inner architecture, but they are different in the inputs and outputs. The first two networks take a grasp-centric depth image and object center of mass location as inputs and output the estimated lifting robustness and displacement. While the third network also takes in two additional binary masks that represent high-cost and low-cost areas for grasping to reduce sample complexity. It also takes in the estimated displacement produced in the second stage. We train those three networks in simulation and evaluate them in real world. We designed a system that procedurally generates three categories of tasks: bracket cone insertion, gear pack insertion, and ship insertion. We generated 5,000 parts for each of the tasks. In real-world evaluation, we use both generated and real parts with the Epson C4L robotic arm. We use Coppelia Sim to collect randomly sampled grasps for each of the tasks. We record a depth image, object displacement caused by the grasp, and also an insertion error during each trial. In total, we collect 0.7 million trials to train our three networks. We form the training as a curriculum learning problem. The idea is to start learning with easy data points and increase difficulty gradually. For brackets, the error is the distance from the corner to the insertion frame of the bracket. We use 4 decreasing threshold to determine whether an insertion is successful. For gears, we use 6 packs of increasing diameters so that the clearance decreases over time. Similarly, we use 4 slots of decreasing clearance for each of the ship's insertion tasks. Here is the training curve for all the 3 tasks. We train each curriculum step for 50 epochs, and we compare it against training directly. Note that for both training as curriculum and training directly, we use the same set of data for validation, and this set of data is labeled with the hardest threshold. We can see here, training as curriculum always outperforms training directly, and at the last epoch, there is an about 10% improvement. Now we have 3 networks. The first one estimates picking up robustness. The second one estimates post-grasp object shift, while the third one estimates insertion robustness. We make 3 ablation baselines to check whether each component works as expected. The first model only has the first network, the second model has the first 2 networks, while the third model has all 3 networks. Here are the performance for each of the model. The last bar is the performance with all 3 networks tested in real world. All the other bars are in simulation. The first figure shows the lift success rate, while the next 2 graphs shows the estimated translational and rotational RMSE. We can see that Model 3 has the best performance and Model 3 has all 3 networks, and it also transfers well to real world. And this figure shows the insertion performance for all the 3 tasks. Here Model 3 also has the best performance compared against the previous 2 networks. In conclusion, we proposed a method to plan robust, precise, and task-oriented grasps by training 3 cascaded neural networks. We also showed that this policy, which was trained in simulation, also deployed in real world without the need of further fine-tuning.